Okay, we've got a couple of topics that we need to cover before the final exam, and this one is actually a very important topic to talk about. So what we're going to talk about today is, and I don't have any slides that I'm going to go through. I'm just going to lecture this the old-fashioned way. I'm just going to make it up as I go along over the next hour or so. We will have a lab next week that will regard this, and actually it will be a lab. It'll be the start of your final mini project. So today's lecture is kind of leading to the mini project and I'll post the mini project before, I'm going to say before Monday. It'll be over the weekend. I'll probably post it. What? Before next Monday. Yeah, but I won't. But it's going to be similar to what I'm talking about today. But the mini project is actually going to be using what's called a finite state machine. And we have not covered a finite state machine. Finite state, I forgot the word state right there. I knew something didn't look right. Now, a finite state machine basically means that we're going to be going through and we're going to define certain states that our, quote, project can be in. And probably the easiest one, what's that beeping that there is? Anybody know? Is that my phone? Out there, it sounds like it's coming from the hallway. Out there. Is if we look at an elevator, right there. An elevator's got 3 floors, right? So it's got 2, 1, and ground right there. So now we can represent this in this way: G, 1, and 2. So if it's in ground, we've got 2 choices. We can either stay in ground, or we can go to the first floor, right? Now, the only way we're going to go to the first floor is if somebody, and we'll talk about this in a little bit more detail, but we've got some other things to talk about. When we're on the first floor, we can do 3 things. We can either stay on the first floor, go back to ground, or go to 2, right there. When we're on the second floor, we've got 2 choices. We can go back, or not go, but stay in 2, right there, or go back to 1, right there. We don't allow the transition of ground to 2 directly without going through 1, and we don't allow the transition of 2 to ground without going through 1. So we've got that there. So now a typical elevator, for sake of argument here, I'm going to say we've got an up button, a down button. These are our 2 inputs right there. We've also got 2 outputs. These are in, right here. And we've got outputs. We've got a up motor and a down motor. Now, we could argue that there's 1 motor and we shift the transmission to go up or down, but we can simply, for sake of keeping things simple, we're just going to simply say that we send a signal of up to the motor to tell it to go up. We send a signal to down to tell it to go down. And with 1 pulse, it only goes 1 floor right there. So this is a typical state machine with 3 states right there. Now, we can design state machines with any type of computer logic we want right there. But since this is a course in embedded controllers or microcontrollers, and we're using C, we would use C to do that with that there. So, and I'll go into more detail of this probably next week, but the programming, actually I'll probably go through a little bit of it today. So we can look at another example, and I don't have examples, so if I do the programming today, keep in mind that it may be some syntax errors in it because I'm doing it off the top of my head. I've done it many times, but I've worked with too many languages over the years. Well, another example, and this is a typical example, is a standard stoplight right there. So I'm going to just kind of write a problem in in kind of a very loose notation that there. In other words, I'm going to use text and explain it, but it's not going to be that there. But we're going to have a stoplight that there. And our stoplight has a north-south set of lights right there and an east-west set of lights. And each set of lights has got a red, a yellow, a green, a left turn, a right turn light that is on when you can do a right turn, that there, and the same way here, red, yellow, green, right turn. We don't have a left turn light, So again, I'm just making up a stoplight that there. I could go to any particular intersection here in KL, and I could probably look at the stoplight, and there doesn't seem to be any standard from what I can tell. I'm used to a U.S. standard, but in Malaysia, I don't see a whole lot of standards up there. And then I'm going to also put a north-south right turn sensor in there, and an east-west right turn sensor. And what these sensors are is they're little plates underneath the road that if a car is in the lane to turn right, it will close the switch and tell our microcontroller that somebody wants to turn right, so on the next cycle to go through a right turn sequence. If there's no car in the right turn sequence, then ignore it. And this is actually probably going to be your midterm, your course project. I have to think about it, but it's going to be something along this line. So our states, and I'm going to just list our states instead of going through the bubble graph right there. And so our states are, and I'm just going to put in some order. We're going to assume that we're going to start out, our initial state is going to be a red state right there. So I'm going to assume that our states are going to start off with, I'm going to say north-south, red, east-west, red. And that there. And when we get into how we define our states, we'll get into that there. But this is going to be a state where we're going to wait for 2 seconds. Right there. This is kind of a state that we're going to go through this every time just to clear the intersection, because one thing I noticed is that people like to run red lights right there, or right there. Or they like to, I shouldn't say run red lights, they like to, when the light is green and it turns red, they tend to go for a few more seconds afterwards. Sometimes quite a few more seconds afterwards. That there. So we're going to always have a red cycle to just kind of give people a chance to clear the intersection. That there. Then our next state is going to be a north-south. Right now I'm going to, for our first example, I'm going to ignore these sensors right here. And I'm not going to worry about people turning right. I'm just going to do a normal 4-way stoplight with just a few states here. North-south, green, east-west, red right there. And we're going to wait here for 30 seconds right there. In other words, this particular light, traffic that's going north and south, it's got 30 seconds that there, and then we go to a north-south, yellow, east-west, red, and we're going to wait here for, we're going to say a yellow light, 5 seconds right there. Right there. And then we're going to then do our east-west red, north-south red, and we're going to wait 2 seconds right there. So in other words, we're going to go through and we're going to just wait 2 seconds for this to occur. Right there. Our next sequence is going to be east-west green, north-south red, and we're going to wait, we're going to say 20 seconds. again, we're assuming that there's less traffic going east and west and north and south, so they only need 20 seconds to clear the intersection right there. Then we go through our east-west yellow, north-south red, and we're going to wait, again, 5 seconds. Right there. And then we're just going to go back to the top and repeat. So this is a simple stoplight program right there. So, you know, and again, the way that this looks right here on the bubble graph, and the bubble graph, actually the table is easier for me to understand than the bubble graph on this one. But the table starts off with north-south red, east-west red. We have a little place where we stay for our 2 seconds. Then we go to our next one. We have our wait. We go to our next one. We have our wait. We go to our next one. We have our wait. And then I think there's like, and then we go back to our beginning. That's our bubble graph right there. The table actually makes more sense to me right there. So, that there. You know, so if you read a lot of the literature, most of the literature actually dwells around using the bubble graph. I tend to ignore the bubble graph and go straight to a table. Now, the only place that this falls apart that there is that we have to take into account inputs that may change our transition. This is a straightforward state diagram where we go from one state to the next and we ignore all inputs and we don't allow alternate states at there. And it's very, very simple. As soon as I throw in my right turn signals, things change. Because what happens when I put in my right turn signals, right there, is that we start off with our north-south red, our east-west red, right there. And then we have our wait, and I said 2 seconds. Now we have to put an if statement in. If the north-south right turn sensor, and again, I'm just making these variable names up, right here, equal 1, that means that there's a car in there. We want to go to north-south right turn, east-west, I'm going to put a G there, east-west red. We do our wait, and we're going to give it 10 seconds for the cars to do the right turn. We do a north-south right turn yellow, east-west red. We give that 5 seconds right there, and our end if right there. So we're looking at the sensor and we're deciding we're going to go into our next, we're going to go into the state. Then we do the same, then we just go through here, and then our north-south, green, east-west, red, and it follows just like the other one. And then after our east-west red, this ... just like what I had listed up above, right there. And then we do our north-south red, our wait, 2 seconds right there. And then we do our if, east-west, right turn sensor, equal 1, right there. Then we do our east-west right turn green, and you don't necessarily have to put the north-south red in there. I mean, these variable names get long, right there. And at there, wait 10 seconds again, or whatever, at there, east-west right turn yellow, right there. Now, right there. Now again, this right here is a state name. That's where we're at in the states. Now, when we're in a particular state, we want certain things to happen. That there. normally what I say is that I usually do my code right there where I set the lights equal to something right there in this particular case. So I'm going into a little bit more detail on this one here, right there. So whenever I do this here, then we're going to say wait 5, and if, and then we go on that there. That there. Now, whenever I do this, what we want to do is that I could do a function call here. So I write a function for each state, and or we just simply say lights is equal to, since the only thing we're going to be doing is changing our lights right there. So in our stoplight program, we're going to, first off, we're going to define, I'm going to call it port 1. I don't have my board with me to remember which ports the lights are on that there. But port 1 is our light port right there. And does our board have 1 or 2 push buttons? I think it's only got 1, doesn't it? Yeah, it's only got 1 push button, is that right? So I may have to simplify the program to just use 1 left turn that there. So port 1 is lights that there. So, and again, the push button I can't remember off the top of my head whether it's on port 1 or 2, or port 0, 1 or 2. We got 3 ports available and only a couple pins on port 2 right there. I can pull up the data sheet, but it doesn't matter right there. So we've got our right turn sensor right there. And again, the project will be toned down if I decide to use this for the project that there our push button right there. So whenever I simply do that, first off, the way that you're going to encode this is you're going to set up an enum, an enumerated type, and you're going to call it states right there, and then you're going to list all the possible states. And I'm not going to go through the C code today on how to do that. I'll pull up an example next Thursday when I officially go through this, but I'm going to start this. I'm going to put the assignment up first so that you look at it, and in the assignment that there, and today's discussion is just introducing finite state machines. I don't expect to cover everything on finite state machines in one lecture. You won't remember if I did. I could, right there. But we define what our possible states are. So one of the things that you need to do whenever you're going to define a finite state machine is you have to first off list the states right there. And they have to be inclusive. And one of the rules on this here is that every state has one possible set of outputs right there. So in other words, I can't have a single state that allows the lights to be anything other than red and green. I'm going to say red is our north-south and green is that there. Or a state has to have the right turn light is yellow going north and south, and the east-west light has to be red. A state has to have one set of outputs right there. So we have to list all the possible states, and again, pick names that make sense. I've been using names such as north-south right turn, G, east-west red. Again, this part of the name doesn't have to be there, but the primary part name has to be there so that they make sense right there. So that's your first thing, is you list the states. Then the next thing you want to do is you want to list the transitions right there. What are your possible transitions? Going back to my very first discussion of my elevator, I define my transitions here. This is my possible transitions right there. And you can do that graphically, or you can do it with a table right there. Sometimes it's easier to do this graphically because you can have some complex transitions that a table doesn't necessarily show. I'm keeping it simple for this class, but state transitions can be extremely complex. And I've got another example that I'm going to talk about up there. Again, today I'm not really emphasizing how to write the code. I'm just emphasizing how to think about what the state machine is going to do, and then how you translate the code, translate this state transition table into code, how you define the select case, how you write the select case there, how you would set up a bit up there, is totally dependent on what language you're using, what technology. I've done finite state machines using TTL logic with Karnaugh maps. I've done them using VHDL up there. I've done them using C. I've done them using assembler. That there. The thought pattern to designing the state machine is the same no matter what technology or language you're going to use. So that's all I'm talking about today is what does a finite state machine look like right there. So now the next thing, part of the transitions that there is that you're going to be, you list your transitions, and this could be either with a transition table, or it can be with a bubble graph. Now, a bubble graph looks like this right here. A transition table looks more like this right here. Now, normally if I do a transition table, I will use Excel, and I'll go through and show you how to do that next Thursday. So next Thursday, I may or may not do a lab session. I may just do another lecture section to follow this up. I'm going to make this actually do the end of revision week. So you've got some time. Now, I know some of you go home over revision and you think you're going to work on these things. If you're going to go home, I recommend you have it done before you leave campus. Because I know how well people work on these things at home. Because I'm guilty of taking work home on Friday, thinking, well, I'm going to get this done over the weekend. Come Monday morning, it's like, oh, crapola, I forgot to do this. I know last Friday, Ibrahim gave me a stack of final year papers to review. That first FYP, this is final year paper. FYP 1 to grade over the weekend, and the trouble was this weekend we had Saturday, Sunday, Monday, Tuesday. So I'm thinking 4 days I'll get it done. Well, the worst thing I've ever discovered is as soon as you give someone too much time, it gets forgotten about. I made the mistake, with my scooter. I took it in to have it repainted and some, repair, some stuff done on it. Because the first 3 months I owned my scooter, I was pretty rough with it. I'm learning how to ride a new bike. I never owned a bike before, so I had some scratches and some things that I wanted to do. Nothing major, but it was a job that the shop could have done in a day. And then the repair. Actually there wasn't any dents or anything that needed to be done. I just wanted to repaint the scratches and replace one little piece of trim that I scraped against my wall parking it at home. It was a thing that he could have done the repairs in probably about 45, 30 minutes, painted it, let it dry, and put all the trim back on, and had it like a day and a half or so. I gave him a week and a half to do it, and he didn't start it until I came back and called. So that's why I'm saying I'm afraid I'm going to give you too much time that you'll put this on the back burner right there. Okay, but also part of the transition is that you also need to have your inputs defined. Because your transitions have are related to your inputs right there. Going back to our beginning one right there, our elevator right there, and at there, when we look at our elevator right here, we have, again, I'm going to just go through the elevator again, is that we've got three states, G, 1, and 2, right? We've got inputs, I'm going to call it up B and down B right there. Those are our two push buttons. We have two outputs right there. Right there. So our two outputs are there, and I won't worry about the outputs right now. We don't care about the outputs right there. But our transition right here, I'm going to show this here, and I'm going to say up B equals 0. Until I hit the up button, I'm not going to go anywhere. Right there. Here, up B equals 1. I put that right there. So that defines how I move from one state to the other. Here, this one's more complex because this one here is up B equals 0, down B equals 0. They both have, if I hit the up button or the down button when I'm on one, I'm going to do something. So this is an and situation right here. So we have to define that we're going to stay in this particular state as long as neither button is pressed right there. So now we come back over to here and we go back to here, down B equals 1. Here we go up B equals 1 right there. Now we haven't addressed the situation where they push both buttons at the same time. We're going to assume that that doesn't exist. Nobody's fast enough to do both. Or we should simply say the down button has priority over the up button. It doesn't matter right there. But we're just going to address that one case. Now when we're in 2, we're only worried about the down button, so down B equals 0, and we go back to here, down B equals 0. So here's how we define our state transitions right there on a bubble graph right there. Now, if we do this in a table, it's more like what I did here. Now here we show just a linear path right there. The only difference is here I've got this if statement right here. Looks like this. Now this here in a bubble graph would look like this right here. And I broke it again. Actually, this okay, right there. From a bubble graph, this first one looks like this right here. And then I'm going to show here 2 states down right there. So this is right turn S is equal to 0. Right there, we go straight to this state. Here, our right turn sensor equals 1. We go here, here, and then we go back up to here. Right here. So this state here is our north-south red, east-west red. And here, we're looking at our sensor. This state right here, and again, this is kind of awkward to look at, is this is our north-south green state right there. And this is our north-south right turn green here, north-south right turn yellow right here. So we look at this right turn sensor. If it's a 1, we go through these 2 states. then we do the normal right turn motion right there. If there's no cars wanting to turn right, we skip that state. Now that's how people get killed, because the right turn, there's no cars in the right turn lane. The pack of motorbikes are all sitting to the front. They all know that they think they all know the way that the lights work, right? That there, and they see the right turn light comes on. They look across the way. There's nobody wanting to turn right, so they go ahead and run the red light, right? That's what happens. And again, I'm not, I didn't grow up with motorbikes like some of you folks did and started riding them at 12. And I know that's illegal, but I see 12-year-olds on their bikes through the neighborhood. I only started, my first motorbike was about a year and a half ago. I bought the Vespa, and I'm starting to do that. I shouldn't admit on YouTube that I run red lights, but and the reason is that it's going through a cycle it doesn't need to go through. And everybody's figured that out, so they run the red light. Well, what happens is they're running the red light, all of a sudden a car comes barreling down that decides he wants to turn right, but he's not in the right turn lane, and he goes ahead and turns right in front of all the bikes, and bang, you've got another fatality, right? So, the way you get around that is you design smarter stoplights, and you use sensors and things like that. But this is the way that we do this right here. So this is another example. Again, I don't want to get into how we write the code. Now, the one thing we also want to do, what I like to do is at the end, I like to just simply do a select case statement to define the outputs right there. Although that's a little awkward to do in C, that's easier to do in VHDL. So we won't do that in C. The reason is VHDL allows parallel processes. And this is a side note. VHDL is a way of designing, and VHDL or Verilog, of designing field programmable gate arrays or customized Cs. And when you design a customized C, you're allowed to set up parallel processes. When we write in C, it does this line, then this line, then this line, then this line, then this line. That's called a sequential process. It goes through and does everything one line at a time. In some ways, this type of programming is easier done in C, because I could do, when I go into a particular state, for example, north, south, red, I'm going to call this as a function right there. And I'm going to have a function here called, it's a type void, and it's down somewhere else in my code, void north, south, red, right there. And int, and I'm going to say lights is equal to 0, 3a x, for example, right there, whatever your lighting sequence is. And then I'm going to call delay right there and pass it 2. And then simply at that point it would return back. And that's how I would define my states, is that we would have, my main code would look like this, while KL not frozen, right there. And that's a global variable we declare, or a constant we declare as 0, in other words, or as 1. Or we could just simply do while 1, right there. Like I said, most programmers I know have some kind of say until while hell hasn't frozen over or something like that. It's a way of just simply that there. And we're just simply going to say north, south, red, east, west, red, right there, at there, north, south. And then we're going to simply say if north, south, right turn sensor equal 1, that there, we're going to call north, south, right turn green. We're going to call north, south, right turn yellow, right there. And then we just in that there, and then we go straight to north-south green, north-south yellow, right there. So you can see our code is actually fairly simple. When you go through the design process, you understand what's going on that there. So this is what your code is actually going to start looking like in your main, right there. Now you still have the overhead of setting up your lights and all that there, but but again, when we look at here, lights is a variable that we set right there. It's going to be equal to port 1 or port 0 or whatever port we use, and we're going to output whatever our lighting pattern is, and we have to define what those are right there. In other words, when we look at those lights, that's my next example here, but right there. But again, what we're looking at here is this is what our code is going to kind of look like as we go through our design. That there. So doing our state transition table is really getting us ready to write the code. Writing the code is the easy part. Once you have the template for the code, it's fairly easy. That there. Because all you do is you list your states, and you have an if statement that tells us where to go next, right there. So that there. Now again, sometimes you have to do things a little bit more complicated, and another way of doing this is do with a select case right there. And a select case simply means that select blah 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 that there, and I can't remember the syntax, but I'm going to say case north south red east west red right here, right there colon, and then we declare two variables. One is current state and one is next state. Right there. And when we do this, we would then say if north-south right turn sensor equal 1, we're going to say next state is equal to, and whatever the next state would be. In this case, it is north-south left right turn green right there. And then we're going to say lights is equal to whatever 0A, 3H, or whatever right there. And then we call wait 2 or delay 2, whatever we want to call it. They give us our 2-second delay right there. And then we have our next state we list here, but we have this option right here of putting our next state right here. And we tell it what our next state is. And that's easier for much more complicated transitions. Right there. Right there. And I'll go through a little bit of how you would code this. This is the normal way of implementing a finite state machine in C, because we have no idea how complex a finite state machine is going to be when we start off normally. We could do ours very simple like this right here, because if we're doing a stoplight now, and again, I haven't decided whether I'm going to do the stoplight or not. If I decide I'm going to do something like a washing machine, which I've done in the past, that there, and I'll talk about what a washing machine would look like, a dishwasher, a refrigerator, household appliances, a toaster oven, all these various things, all can be done with finite state machines. Probably 75% of embedded control systems use some form of finite state machine control. So I'm kind of skipping through it towards the end of the semester, and I probably should move it up more toward the beginning of the semester. That there. Another example of a finite state machine is, this is a classic one, right there. Right here. This is the classic vending machine. I have the El Cheapo UniKL vending machine. That there. And it's so cheap that they actually stole it from the U.S. and they have to use U.S. coins. That there. Well, we won't say it's. We can modify it that there. That our states are going to be 0, 50, 0. Oh, this is the one that I can't write on here. Because when I write on this one here, right here. Yeah, no, I can't write on this one because the screen resolution with PowerPoint got there. But on our finite state machines right here, I'm going to say 0, 50, 50, 1 RM, 150 RM, and 2 RM. Right there. So we're going to assume that actually you would stop at, well, yeah, we could do 2 RM at there or at there. But, you know, this uses American coins, which are 25-cent pieces, called a quarter. And the reason it's called a quarter is 1/4 of a dollar right there. So, and we've got a soft drink, a Coca-Cola or Pepsi or whatever, and it costs 75 cents right there. And that's actually, yeah, actually, when you look at the prices in the U.S. versus Malaysia, 75 cents now is 150. Oh, jeez, it's over three ringgits for a Coke at 75 cents. That's a pretty cheap Coke sheet anymore on campus. I think my last campus they charged $1 for a Coke, so that would be 4 ringgits and 40 cents for a Coke out of the vending machine. Now you know why I moved to Malaysia, right? Out there. But regardless, this particular vending machine charges 75 cents per Coke. And you can put in a quarter and only a quarter right there. It doesn't take 10-cent pieces, it doesn't take 5-cent pieces, it doesn't take 50-cent pieces. That's why it's a cheap machine right there. And it will also take a single dollar bill right there. It's got a dollar changer right there. So that there. So again, the goal here is we've got 2 buttons right there. One button is dispense my Coke. The next button is give me my money back. So we've got 2 buttons on this machine. We've got 2 outputs. One is kick back the money. The other one is kick out a Coke. In other words, give me my refund. I put in 50 cents and I realize I don't have a third quarter. I hit the refund button and I walk away without a Coke. I put in my $1 and I look at the Coke and I say it's not worth 4 ringgits and 50 cents. So give me my $1 back. I'm going to go down and buy it at the grocery store for 15 cents instead of $1. There's a huge markup on vending machines in the U.S. Huge markup right there. So this particular problem here is we've got our states where are actually defined by how much money is in the machine right there. So we've got one state here for we haven't put any money in. Here we put 1 quarter in. Here we put 2 quarters in. Here we put 3 quarters in. Here we put in a $1 bill right there. So again, we're looking right there. So this is showing our transitions right there. Right there. So we put in a quarter, we put in a quarter, we put in a quarter, we put in a quarter. Right there. So that's our possible transitions. We can't put in more than $1. Right there. Now we also have a transition where we could just stay in our current state or put in another $1 right there. And then we have our transitions here where I push the soda button. I push the soda button. Now our push your soda button right here, this particular El Cheapo machine gives us our soda and also shows we still have a quarter left as far as credit in the machine right there. Then the next one is we push our return, which then kicks our money back right there. Now they show this little bubble, this little brown here, which means we're going through the state of kicking out a quarter, kicking out a quarter, kicking out a quarter until it's equal to 0. But this is another type of finite state machine. But the reason I put this here, discussed it, is because this shows a more complicated state transition, because I can go here, I can go from $1 here that there to the refund, or I can go to the soda and the refund. I've got all kinds of options that can happen that there. So another one I used to do a lot in I'll just go this way here, is that one of the ones I always used to go through before was, something that you've never seen before, because they quit making them before anybody in this room was born, and that was a VCR. A VCR was a video cassette recorder, right there. So it had big tapes up there, but we would have an idle mode, right there. We would have a play mode. We would have a fast forward mode. We would have a fast forward play mode, where it's kind of like it's in play mode, you hit the fast forward, and you see the movie go twice as fast or 3 times as fast. You can do the same thing with your iPhones and and hit the fast play mode right there. But this worked on tapes. We also had a rewind mode. We had a rewind play mode where you could play it backwards fast right there. We also had an eject mode. And I can't spell the word eject right there, where we eject the tape right there. We push the tape button. We also had some inputs here. We had our buttons. We had play button, eject button, fast forward button, rewind button, right there, stop button, right there. And we could design this thing to go from one state to the other. And this would be a very complex, because if it's in the play mode and I hit the fast forward button, it would go to fast forward play. If I'm in the play button and I hit the mode and I hit the rewind button, it goes in the rewind. That's there. If I'm in the idle mode and I hit the fast forward, then I'm going to go into the fast forward mode right there, where I wind the tape back very quickly, fast forward. If I'm in the idle mode, I hit the rewind button, it goes very fast. It does the rewind, and rewinds the tape back to the beginning. And again, this might be a concept that's difficult to understand, because many of you have never seen tapes. Has anybody ever seen what I mean by a tape recorder, cassette tape recorder? Out there. But it's a magnetic, it's a magnetic medium that's wound on a spool, and it contains either video or audio or data, and you can fast forward, rewind, or play right there. It's been since replaced by the DVD which has since been replaced by MP4 files, or MKV, I think is the newest format there. So the cassette tape, this actually was an assignment I used to give in my, in one of my early VHDL courses there. I quit giving them because nobody knows what a VCR looks like right there. But this is another example there. This is actually a fairly difficult problem right there, because of all the various transitions there. Although you might be surprised, I gave this to technology students as freshmen there, and most of them were able to get it done. So there. Another example is, and this is one you may end up getting, is a standard washing machine. I may go out there, and I actually got a washing machine dryer there. It does the wash cycle, then it does the dry cycle afterwards there. So it's got a various set of modes right there. And this is one I've used on this campus before. Again, it's got the idle mode. It's got the fill mode. And I'm going to give it a wash fill right there. It fills for wash. It's got the wash mode right there. It's got the wash drain mode right there. And these are all states right there. We've got then the rinse one fill mode right there. We got the rinse one mode state. We've got the rinse one drain mode right there. We've got the rinse two fill mode right there. The rinse two mode. The rinse two drain mode. The spin mode right there. And then we go back to all the way back to the idle mode right there. Now this particular one's got a lot of inputs and outputs, so that's why it's an interesting one right there. And we also got, our inputs might be the start button right there. Now again, this is the El Cheapo UniKL washing machine. It doesn't have any fancy cycles, no gentle or nothing else. It just washes clothes right there. El Cheapo. If we want more features, then our state machine gets more complicated. But we have a start button, we have a stop button right there. And our stop button is going to drain it, and then there when you hit the stop button right there, we've got some input. Another input might be the full right there. The machine is full of water right there. We've filled it. We're ready to start right there. Again, this is an El Cheapo. It's only got one level of fullness right there. We've got the empty to tell it that the washing machine is empty right there. And we've got the door switch. That's there so someone doesn't open the door while it's spinning and stick their hand in and break it off. U.S. lawyers love that when people can do that, because then they can sue right there. And then you've got washing machines where people like me take the switch out and short it so that you can do it right there. We've got some these are all various inputs right there. Outputs. We've got the fill valve. We've got the drain motor, pump. Believe it or not, you can just open a valve to let water in, but you've got to pump it out right there. And we've got the motor. And the motor, I'm going to put a bracket right there, because the motor has two different states. It can either be spin mode right there, or it can be wash mode right there. Wash and drain are the same mode right there. The agitate mode right there, where it goes this way, right there. The spin just goes around in circles very fast in order to get the water out of the clothes right there. And then we've also got a timer. We would have timers built into our software right there. But again, this is a much more complicated finite state machine right there. And I have used it as the mini project for this class right there. And then there's a variation of that, which is the dishwasher right there. Again, as I said, you can walk around your house and you can look at almost anything there, and you can come up with finite state machine type problems right there. So, again, if you were to do this, then you'd have to do a state transition. I can go from wash, fill, back to idle. If I hit and I'm going to put another button here. I'm going to call it abort. The button right there. The stop button just stops it from what it's doing for right now, so that you can open the door. The abort button drains the machine, and it just stops the operation, so you can put more clothes in or whatever. So I'm going to put an abort button on this one here. Right there. So, but this particular project is actually a little bit more complex than the standard stoplight problem. We don't have a lot of time, so I'm looking at doing a simpler project right there. But again, I've given this to freshmen in the U.S., and they actually have no trouble with this particular problem. So, when you look at these problems, you have to look at them, and once you understand the process, this problem is actually no more difficult than our stoplight problem in terms of the technology that we're doing. It's just longer, right there. Again, when we look at a particular mode, say we're in the wash state right there. Here's our wash state. We're going to stay here until our timer is equal to 0. In other words, it's counting down. Actually, we just have a delay there. And we go from wash there to wash drain right there. And we stay in drain until empty is equal to 0. In other words, it's not empty right there. Once it's empty, then we go to R1 fill right there. and we stay here until full is equal to 1 or 0, until full is equal to 1, and then we go to, the problem's longer, but the design techniques are exactly the same. So that there, and I'm just showing this as a bubble graph. We can do this as a state transition right there. We're in wash mode right there. Right there. Our next state is equal to wash drain right there, and delay, and I'm going to say 15 minutes right there. Our next one is drain, wash drain. Our next state is equal to R1 fill right there. And then we're going to say while empty not equal to 1 right there. And this is just simply a wait state until empty is equal to 1, and we just set there. And so our, once you know the transitions that there, writing the code is fairly straightforward. Matter of fact, when we look at our bubble graphs here, right there, one of the things that is that there's actually a program out there called StateCAD, where you can design the software, draw the bubble graph. You specify your inputs and your outputs, and you specify which outputs are going to be high in what state. You specify what inputs have to be in high or low to do your state transitions, right there, and you draw this huge bubble graph, and the software itself will then write the C code, or the VHDL or the Verilog. So going from the bubble graph to the code is fairly straightforward, and it can actually be done by software. You don't need a programmer anymore. All you need is somebody who's smart enough to draw the bubble graph. The programmer is completely irrelevant out there. And then, of course, the programmer has to set up the inputs and the outputs, and put them all in the proper mode that they're, set up the I/O ports, go through the configuration wizard and set up any that there. But the actual code itself, the bulk of it, is actually written by another piece of software. And another reason why programmers are required to do much more complex jobs than they used to, because the trivial stuff is actually done by other software. And I think I've actually have talked about my normal hour, haven't I? That there. Again, I'm going to post the actual assignment up over the weekend, if not before the weekend. That there, I haven't decided what it's going to be. That there, but I will go through in more detail how the C code looks on the 8051. Today's lecture was more on just what a finite state machine looks like and how to think in terms of, you've got a project that's going to do X, Y, Z, that there, and again, you're going to run a refrigerator, a dishwasher, a washing machine, a set of stoplights, an electric car, a robotic car, right there, and you're going to design a finite state machine that is going to say, this car is going straight, it's following us. Now, let me just kind of go through this example that there. This is one that okay. Another example that there, and this is one that I've actually taught an online course over the years many times up there, ECT 365 up there. And this particular course, the project is to design an electric robotic car right there. They say robotic, but it's actually just a car. And the whole idea of this car is that, actually, do I have it? Oh. Yeah, okay. This is the project right there, and the car just follows the track right there. This happens to use another microprocessor of similar capability of the 8051 right there, and it's got two stepper motors, or this one's got servo motors on it right there, or DC motors. It doesn't matter. You can use any kind of motor that you want with it right there, but it's got two different motors right there. This is actually the one that this is one of my students who submitted it. It was an online course right there. But going back to, and he's just showing that it can go both directions right there. So, that there. But the whole idea of this particular project is that I've got two motors right here, two motors, and they can go at different speeds. I can turn one on, turn the other one off right there. And it's also got a track here that with two optical sensors right here, an optical sensor and an optical sensor here, that looks down there, and if it sees the black here, it knows to turn that direction to get back there. If this one sees the black, it knows to turn the other direction right there. So we've got three modes: straight, right there, left, turn, which when I say left turn, it's not turning, but it's going to lean toward the left because it's supposed to follow the track, and right. Turn right there. So it's got three states right there. And what it does is it says if sensor 1 equals 0, and again, and sensor 2 equals 0, then next state equals straight right there. If sensor 1 equals 1 right there, and I'm just going to say, and again, this syntax is right, sensor 2 equals 0, we're going to say next state equals right turn right there, and this is all else if right there, else if sensor 1 equals 0 and sensor 2 equals 1, next state equals left turn right there, else if sensor 1 equals 1 and sensor 2 equals 1, next state equals stop right there. I didn't put stop as one up there, but that means both it's off the track completely right there. It's, there's both of them that they're ordered. So again, the whole idea is that we're representing this is a finite state machine on how to follow a track. We define what our states are, and our states are, one motor's turning, the other motor's turning, both motors are turning, no motors are turning. Those are our four possible outputs. So we have four possible states right there. I mentioned three up here, but we've got left turn, right turn, straight, and stop right there. Those are our four possible states. And we look at our two optical sensors to determine which state we want to go into right there. And again, that was a sophomore level course right there, or junior level course where I've done that there. So, all right, now I'll go ahead and let you go right there.